you have finished the last in-class exercise question, you can start this section 5. So for in-class exercise 3, number 5, we need to conduct a significance test for B weight. The research hypothesis is that B star does not equal to 0. The null hypothesis is B star equals to 0. Then we need to compute the standard error of B. The standard error of B is 3.46 and the standard deviation for X is 1.58. B weight is 3. Standard error of B is 3.46 divided by 1.58. Multiply square root of n minus 1. It is 1.09. The t-score for the B weight is B minus B star divided by standard error of B. So it is 3 minus 0 divided by 1.09. It is 2.75. From the t-critical table, degree of freedom is n minus 1 minus 1, which is 3. T-critical score is 3.18. Therefore, we fail to reject the null hypothesis. Now, we need to construct the ANOVA table and conduct the F-test. ANOVA table is called a source table. It integrated all the elements we have been doing onto this table. We know that the true y value equals to the predicted y plus error. In mathematical terms, the sum of the squares for y equals to the sum of the squares for predicted y plus the sum of the squares for error or SS residual. In other words, SS total is the sum of squares in the true y's equals to SS regression plus SS residual. So for this table, the left column presents regression, residual, and total. Then the second column, we should plug in all the sum of the squares. SS total is SSY, which is 126. SS residual, we have it, is 36. Then SS regression, or sum of squares due to X, is 126 minus 36. It is 90. DF total is n minus 1, which is 4. DF residual is n minus 1 minus 1, which is 3. DF regression is 4 minus 3, which is 1. The next column is called mean squares. It is the sum of squares divided by DF. Mean squares for regression is still 90. Mean square for residual is 36 divided by 3. It is 12. We don't need mean square for total. F-test is simply the mean square of regression divided by mean square of residual. So 90 divided by 12 is 7.5. F-test tells people if X explains a significant amount of variance in Y. In other words, it tells if X is a significant predictor of Y. F-test, as we mentioned, it equals to mean square regression divided by mean square residual. So it is 90 over 12, 7.5. It tells if X explains a significant amount of variance in Y. If we have just one predictor, this F-test test essentially is the same thing as the t-test for the b-weight, because t-test for the b-weight also tells us if x significantly predict y. So when we have just one x, f equals to t squared. So t score for the b-weight was 2.75. We just had it a couple pages ago. So if you square 2.75, it is exactly 7.5. And in this case, it was not significant. Both f and t-test were not significant. So x is not a significant predictor for y. In other words, if we have more than one predictors, t-test tells us if a predictor is a significant predictor. F-test tells us if a collection of these predictors significantly predict y. In that case, t-test will not equal to f-test anymore. Here is the SPSS output. So I just use SPSS to run regression, and it gives us these main three tables. So the first table I listed here is the coefficient table. In the SPSS output, this was actually the last one. I just flipped the order of the table. Here lists the coefficient. Here labels unstandardized coefficients. So the number next to constant is the intercept, A, and the number next to x is the slope. So B is 3, A is -8. Then the number under standardized coefficients is labeled as beta. So this is beta, which is 0.845. 1.095 is the standard error of the slope. Then t-test equals to 2.739. Our hand calculation was 2.75, so it's similar. And then p-value for this t-observed score is 0.071. The second table is the ANOVA source table I just showed you. So SS regression, SS residual, SS total, DF regression, DF residual, DF total, mean square, this is the F-test, and the p-value for F-test. As you can see, it is the same thing as the t-test. If you square 2.739, you will get 7.50, and the p-values are the same. The last table is the model summary for one predictor in predicting y. Correlation between x and y is 0.845. Do you remember what does the correlation equal to? The correlation coefficient equals to the standardized coefficient. That is R equals to beta. This is R squared. So R is the correlation between x and y. When we square it, when we square 0.845, we will get 0.714. It is a very important figure, 0.714. Let's see what R squared tells us. R squared is the ratio of SS regression and SS total. In other words, it is what percentage of y, variance in y, is predicted by x. What percentage of variance in y is being predicted by x? So R squared is the proportion of variance in y due to regression or due to x. Then if we conduct a significant test of R squared, then R square equals, the F-test equals to the R square, the proportion of change in Y due to X, divided by number of predictor. In this case, it was just one predictor of X. This is the denominator. The denominator is 1 minus R square divided by N minus predictor minus 1. So the top is 0.845 squared divided by 1. Bottom is 1 minus 0.845 squared divided by 5 minus 1. We will again get 7.5. It is the proportion of variance in Y due to X is that significant, and this F-test was not significant. R square is the proportion of variance in Y due to the regression. Look at our example of the stress and the symptom. The correlation between stressor and the symptom is 0.529. R square is 0.279. R square equals to SS regression divided by SS total. SS total, the denominator refers to the total variance in Y, and SS regression refers to the variance explained by X. So this 0.28 represent about 28% of the variance in symptoms can be predicted from variability in stressful event. Therefore, R square is a very straightforward way to explain what percent of variance in Y is being predicted by X. And it is very useful in even daily life. When my sons were little boys, I was interested in developmental psychology. I want to learn about developmental psychology. I read this blog written by a big name developmental psychologist. One day he wrote something very interesting. He said that there is a longitudinal research study couples IQ. Over 20 years of research, they found that couples IQ is related, has been changed, has been changed. The change in one person's IQ is positively related in change in another person's IQ. The correlation coefficient is 0.20, and he pointed out that couples' IQ do change over the years. About 20% has been changed over 20 years. So when I first read it, I found it is pretty awesome. So if you marry somebody smarter than you, over the years you could be smarter. 20 years later, you could be 20% smarter than your own IQ. That's very big. Then I thought about it. It's just a correlation. It is not R square. So we would need to square the correlation coefficient. If the correlation coefficient is 0.20, then when we square it, it is 0.004. That is, over the 20 years, a couple's IQ could change 4%, not 20%. That makes more sense. So when you think about R square, you need to really understand what it means. Then guess which direction the IQ is changing. Does it change towards the person who's smarter, or it changes toward the person who is less smarter? And the research found that it changes toward the person who plays a dominant role in the family. Okay, summarize the lecture for today. We talked about B weight, beta, and the correlation coefficient. We introduced the standard error of estimate. We learned how to test the significance of B weight. We talked about ANOVA table, the source table, and the F-test. Finally, we introduced R-square and the significant test on R-square. You should have finished in-class exercise 3. You need to hand it in to Eric next class. And you will also work on lab 3 as well as the homework 3. Okay, that's it. I hope you have a nice week.